Hello and welcome to another week of ECE 108. This week we're going to talk all about various proof techniques, so let's jump right in. Before we jump into the proof techniques, let's talk about what a proof is. So a proof is simply a series of convincing arguments that leaves no doubt that a given proposition is true. So a natural question to ask is, why do we want or need proofs? Well, we have science, and science is good enough, right? Well, let's look at a fundamental flaw in science. So we can look at the question, why does the Earth orbit the sun? Well, Newton said that the force of gravity is equal to this expression here, and if you chase out the details, this is an explanation for why the Earth orbits the sun, and you can use it to predict the orbit of Earth given initial conditions. Later on, Einstein came around and said, well, no, this theory, while it works in some cases, isn't fully accurate for things like the orbit of Mercury, and thus we need a new theory. So Einstein came up with his field equations, amongst many other things. This equation essentially sets the shape of spacetime on the left-hand side equal to this tensor here that represents the configuration of mass. So we know for a fact that Einstein's theory has some limitations. Namely, we know quantum mechanics is a theory that's very accurate and makes some of the most accurate predictions that we've ever made, and it clashes with Einstein. Therefore, at some point in the future, someone else might be able to solve this problem and build a unified theory. So what's the lesson to be had here? Well, since Newton, Einstein, and someone else in the future, presumably, didn't prove that these laws work for our universe, they're not guaranteed to actually be true. It's just a very, very good model. If I were to be able to prove that, say, Einstein's field equations are actually true in the universe and that's the complete picture, then no one would ever be able to overtopple Einstein. He would have proven that that was the case. Well, in mathematics, we can set down our assumptions. We can say, assume A, B, C, D, and E are true, for instance. And using these assumptions, we can mathematically prove that other things have to hold, given that our assumptions are true. Thus, as long as we didn't make an error in our argument, then if we prove something, it will stay true for all time, again, given that those assumptions hold. Someone in the future may come by and say, well, no, I don't believe this axiom. You can throw it away and generate new mathematics without that axiom. And this does happen. For instance, you have Euclidean geometry, so geometry of a flat plane, where we assume that parallel lines don't cross. Well, that assumption does not hold for, say, the geometry on the Earth. So we can generate a new field of geometry. But as long as the axioms of, say, Euclidean geometry hold, then all of the results of Euclidean geometry will be true for all of time. Okay, so let's look at some proof techniques. This week we're going to cover quite a few various proof techniques, so let's give a broad overview of what they are before I spend the next 3 lectures getting into the details. So, logical deduction. So you've already done this a bit. In general, in logical deduction, you build a chain of logical inferences that start from your initial assumption and end up at the desired conclusion. So an example of a logical deduction would be proving that 2 statements are equivalent via algebra. So I start with a statement on, say, the left-hand side. I build a bunch of logical inferences by saying this is equivalent to something else. And then eventually I end up at the logical statement that I wanted to prove at the end, which is, of course, the desired conclusion. Okay, so the next proof technique is case analysis. So sometimes it's easier to take a hard problem and split it into several little problems that are a little bit easier to solve, and that's what case analysis does. So in general, in case analysis, we go through all of the possible cases and show that it's true for each case, therefore it's true for all of the cases together. The next proof technique is contradiction or proof ad absurdum. So here we assume that what I want to prove is false, and then we find a contradiction, which then shows what I wanted to prove is true. So I'll go into the details of exactly what I mean by this when I talk about contradiction later in this lecture, but that is the general idea. So next we have proof by contrapositive. So I know that every implication is equivalent to its contrapositive. So instead of proving the implication directly, I can instead prove the contrapositive. Next, we have proof by construction. So say if you wanted to prove that something exists, one way that you can do that is by simply constructing the thing that I want to prove exists. So in proof by construction, we show something exists by simply building it. Next, we have proof by counterexample. This is more of a disproof technique. If I ask you to prove a statement is true and you find an example where it's not true, then you've disproven it. So in proof by counterexample, we simply show an example where the statement is not true. And finally, we have induction. So here I'm not going to talk much about induction for now, but essentially it kind of ties down into knocking down dominoes. I'll discuss that in lecture 6. So now, this list of proof techniques is not complete. For instance, if something is vacuously true, that can lead to a different proof technique. But between all of the methods in this list, you can prove a lot of statements. So now let's go through some meme-worthy proof techniques. Okay, so I'm not going to go through this slide itself. Pause the video and look through them yourselves. But these are some common methods that you might see in literature or in textbooks, or you might even try yourself. Do not try them. They are not proof techniques. They don't work. So now, before we start getting into the actual proof techniques themselves, I want to comment on mathematics and creativity just a little bit. So, given any proposition, you kind of need to pick one of these proof techniques or more than one proof techniques to be able to prove that statement. This opens the door for being creative. So oftentimes you will need to use some type of creativity to be able to prove a statement. It's not always true, and for many of the proofs that you will do in this next week, you will not need to be particularly creative. But in general, in mathematics in its raw form, there's lots of unsolved problems, and in order to solve them, you're going to need some creativity. And we have this quote by David Hilbert. So, good, he didn't have enough imagination to become a mathematician, and this was upon hearing that one of his students had dropped out of a PhD in mathematics to study poetry. So, good mathematician, not necessarily a good advisor, but this just goes to show you how much creativity you would need if you were to pursue a career in mathematics. Now, with this out of the way, let's get into the details of our proof techniques. So, proof methods, deduction. So, say if I asked you to prove that for every positive integer n squared plus 1 is not a perfect square. So firstly, we need to understand what this proposition is saying. It's saying that if I give you a positive integer n, and I take it square and add 1 to it, that won't be a perfect square. So this begs the question, what is a perfect square? Well, a perfect square is simply an integer n such that n is equal to k squared for some integer k. Okay, so that's what this means. Is it true? Well, I'll just tell you that this is in fact true. So how would you go about convincing someone that this is true? So for this case, you do need a fair bit of creativity, so how would I go about doing this? Well, I know n squared, for some positive integer n, will be a perfect squared. And I know n squared is less than this quantity here. Well, what's the next perfect square after n squared? Well, that'll simply be n plus 1 quantity squared. And if you have questions as per why this would be the next consecutive perfect squared, you can ask in office hours or on Piazza. So now how can I use this to show that this quantity here can't be a perfect square? Well, I can note something. N squared plus 1, well, that's going to be less than n squared plus 2n plus 1. Why? Well, this is positive because n is positive. And finally, this quantity here is going to be explicitly equal to the next consecutive perfect square. Therefore, in this case, my n squared plus 1 is in between two consecutive perfect squares and can't be a perfect square. So now, while you might think this argument is sufficient, in mathematics we want to be a bit more clear and precise in what we say. So this is where the idea of a formal proof comes in. In a formal proof, we write our argument out in a way where everything is defined and there's no doubt that what we wrote is true. So let's write a formal proof for this statement given this kind of scratch work here. So the first thing I do is define all of the quantities that I'm going to be using in the formal proof. So let n be some positive integer. So I'm picking an arbitrary n that is a positive integer. Now I can introduce the idea that these two terms here are consecutive perfect squares. So now I can say by definition, n squared and n plus 1 quantity squared are consecutive perfect squares. So now the reader knows that these two terms here are consecutive perfect squares, and kind of thinking ahead, by reading the sentence, the reader might think that, oh, I'm going to use this fact somehow to prove that this term isn't a perfect square. So now what do? Well, I display all my algebra. Well, this is a series of inequalities and equalities that are true, and it tells me that my term n squared plus 1 is in between n squared and n plus 1 quantity squared, but is not equal to either of them. So now I conclude my proof by saying, thus, n squared plus 1 is between two consecutive perfect squares and is therefore not a perfect square. So this is the framework that you will use for most of your proofs in this course and outside of this course. Make sure to define everything up front and then make your argument here and then finally make your conclusion. So if you have any questions on this proof or the way that I wrote this formal proof, ask on Piazza or office hours. Learning how to write formal proofs does take time. It's kind of like learning a new language. So just keep that in mind as we go forward. Let's look at another proof using logical deduction. So prove or disprove that 1 is equal to 0.9 repeating. Okay, so how could we prove or disprove this? Well, here you need to be creative. So you can pause the video here and see if you can convince yourself that this is true or false. And in the process of doing that, think, why do I think this is true or false? What arguments am I trying to use to prove or disprove this? Okay, so now let's just go in and prove that this statement is true. Well, by a direct computation, I know that 1 divided by 9 is equal to 0.1 repeating. Further, I know that if I take 9 and multiply it by 1/9, I get 1. And if I take 9 and multiply it by 0.1, I get 0.9 repeating. Therefore, I can multiply through by 9 and get that 1 is equal to 0.9 repeating. So this is actually true in the real numbers. You might not want it to be true because 1 and 0.9 repeating have different decimal expansions, but if you're working within the real numbers, these are the same number. There is a number system called the surreal numbers where they are different, but we're not going to get into that. Now, if you don't like this proof, we can have another proof of it. Well, if x is equal to 0.9 repeating, we can multiply both sides by 10 and then subtract x and solve for x to get that 0.9 repeating is the same thing as 1. Further, once you get to geometric series in Math 119, you can either bug Zach to ask him to prove this, or you can ask me and I can prove it for you. Or even better yet, you can go through and convince yourself why this would be true via the geometric series. So this brings up another point. Math can sometimes be unintuitive. A priori, many students would think that 1 is not equal to 0.9 repeating, because why would it be? Okay, so now let's give you some assigned reading. So I want you to read the argument on page 20 under logical deduction. The best way to learn how to prove things is by reading proofs and doing proofs, so I highly recommend that you do this assigned reading. Now let's look through case analysis. So the idea of case analysis is, again, we go through all of the possible cases and we show that the proposition is true in each of those cases. So you've seen this before, namely truth tables. If I have a logical statement that depends on several statement variables, I can build a truth table that contains all of the possible combinations of truth values that those statement variables can take on. And by building the truth table, I examine each one of those cases line by line in the truth table. Before going through examples, I will leave you with a quote. Once you eliminate the impossible, whatever remains, no matter how improbable, must be the truth. This is kind of another way of looking at case analysis. So now let's look at an example of case analysis. Prove that if x is an integer, then x squared does not equal 5. So if I were to try to prove this via logical deduction, I could do that, and let's see what that would look like. Well, I could say, what if x squared is equal to 5? And solve for x. So in that case, x would have to be equal to plus or minus the square root of 5, and these would be the only possible values that x could take on if x squared were to be equal to 5. And I know that plus or minus 5 are not integers. Therefore, if x is an integer, then x squared can't be equal to 5. So there's a few problems with this. One, I'm using a technique that we haven't formally defined yet, explicitly proof by contradiction. And two, this method requires us to use real numbers to prove a property of integers. Generally speaking, it's nice if you stay within the domain throughout your entire problem. Sometimes it's not possible, but it's nice when you can do it. So instead of doing this method here, let's examine cases. So here I can consider two cases. Case 1, I can let x be an integer such that the absolute value of x is less than or equal to 2. Why do I consider this particular case? Well, let's go forward and you'll see. It follows that x squared is less than or equal to 2 squared, right? If the absolute value of x is bounded by 2, then x squared is going to be bounded by 2 squared. But 2 squared is equal to 4, which is less than 5. So in this case, I have x squared can't be equal to 5 because it's less than 5. Now let's consider case 2. Let x be an integer such that the absolute value of x is greater than or equal to 3. So notice one thing. Between case 1 and case 2, I've now covered all possible integers for x. So if I can prove it for the case 2, I'm done. Okay, let's use a similar argument to see if x squared could be equal to 5. Well, we know that x squared would now be greater than or equal to 3 squared, and we know 3 squared is equal to 9, but 9 is bigger than 5, so in this case, I have x squared is greater than 5, therefore x squared cannot be equal to 5. And finally, since between case 1 and case 2 I've covered all of the integers, x squared cannot be equal to 5. So again, tying this to my comment on creativity, you need to be a little bit creative to figure out that this is the way to split things up. And keep in mind, since this is not a math course, I'm not going to expect you to do things that require a significant amount of creativity. Most of the things will be straightforward. Okay, let's look at a real-world example just to show you how case analysis can become very, very, quote, tedious and even computationally too expensive to do, even with modern computers. So the Boolean Pythagorean triples problem. So first you need to define what this problem is. So the basic idea is Pythagorean triples are integers that satisfy this equation. So for instance, 2 squared plus 3 squared is equal to 5 squared would be a Pythagorean triple. Okay, so for some collection of natural numbers, say 1, 2, 3, all of the numbers up to n, can I split this collection S into 2 collections such that neither collection contains any Pythagorean triples? So to better understand this, let's give an example. If S is equal to 1, 2, 3, 4, 5, the only Pythagorean triples in S are 3 squared plus 4 squared is equal to 5, or 3, 4, 5. Therefore, I could split S in a bunch of ways. In particular, I could say one collection will be 1, 2, 3, 4, and the other collection would be 5. Within this group of numbers, there are no numbers that satisfy this equation, and within this group of numbers, or number, there is no triple of numbers that satisfies this expression. So these two sets do not contain any triples. Now, I can ask you, what about this set? So all of the numbers between 1 and 7,825. Is it possible to split it up? And if not, can you prove that it's not possible to split it up? Well, we can try to prove or disprove this via case analysis. But there's a problem with that. There's 2 to the 7,825 possible ways to split this collection up. If you're clever, you can simplify the problem so you don't have to consider all of them. But in either case, there is still a massive number of ways to split this up. It was proven in 2016 that it's not possible for this collection of numbers, but it is possible for all the integers from 1 to 7,824. How did they prove that? They used a supercomputer to go through the various cases. So the proof took 4 CPU years and generated 200 terabytes of raw data. So just to give you an idea of what 4 CPU years is, that would be equivalent to taking 4 computers, like 4 laptops or whatever, and letting all 4 of them run for a year to solve this problem. And to give an idea of what 200 terabytes of raw data looks like, well, your average laptop type thing might have a 5 terabyte hard drive on kind of the high end. They make hard drives that store maybe 20 terabytes of data. They're pretty pricey. But you would need 10 of those 20 terabyte hard drives to be able to store all of this information. So now, if you're interested in looking at more things on this problem, you can read this Nature article on the proof. But the point of showing you this is just to demonstrate that case analysis problems can become very, very large in practice. So now we have a little bit of assigned reading on case analysis. Read the proof of claim 4 on page 21. Now let's examine contradiction. So now let A be a statement. So I know A is either true or false. Thus I can note that either A or not A must be false. One of the two is false. This means that the compound statement A and not A is always false. And I can use this fact to introduce the idea of a contradiction. So the statement A and not A is true is called a contradiction. Symbolically, you can use this symbol to denote a contradiction. Now, we can use contradictions to prove statements. So how do we do this? Well, if I assume not A is true and find a contradiction, then our assumption was false. And since our assumption was false, that means not A is false, which in turn simply tells me that A is true. So now just a definition, a proof by contradiction is a proof technique where one shows that A is true by showing that not A implies A is a true statement. So why does proof by contradiction work? Well, let's use formal logic to prove that A is logically equivalent to this proof by contradiction statement here. Well, how would I do this? Well, A is equivalent to A or A. That's pretty trivial. And A or A is equivalent to not A or A. That's also pretty trivial. Now I can use claim 1 to rewrite this as the implication, not A implies A. So we've now talked about the underlying idea of why proof by contradiction would work. Let's look at a few examples to see it in practice. So prove that there is no greatest integer. How can I do this? Well, let's do a proof by contradiction. So the idea of the proof is we first assume that there is a largest integer. So I'm assuming that the negation of there is no greatest integer is true. Now that I have this greatest integer in, let's build a contradiction. So how can I construct an integer larger than n? N plus 1 is greater than n, and n plus 1 is an integer. Thus, this is a contradiction, so our assumption was false, and therefore there is no greatest integer. So for this case, let's look at a formal proof. Assume for the sake of contradiction that n is the largest integer. You will start all of your proof by contradictions with a statement, assume for the sake of contradiction that something. Now that I have that n is the largest integer, we simply note that n plus 1 is an integer and n plus 1 is greater than n. Now I say this contradicts my assumption that n was the largest integer, therefore there is no largest integer. Now just to comment on the QED square, this is just a symbol that you can use to say you're done with the proof. If you're curious about the history of the symbol, we can talk about it during office hours, but I won't add time to this video by explaining it here. So now let's look at another example. Previously in one of my office hours, I had mentioned that I would prove that there is no largest prime, so let's do that now. Since this is in the proof by contradiction slide, let's prove this by contradiction. Let's assume that there is a largest prime, okay? If there's a largest prime, that means I can build a collection of all of the prime numbers. Thus, there's a finite collection of primes, and I can denote it by P1, P2, all the way up to Pn. So each one of these is just simply a prime number. Now, how could I build a contradiction that this list contains all of the prime numbers? Well, I could consider this number. So take all of the elements in the list, multiply them together, and then add 1 to that product. Now, this is an integer, and it's not going to be divisible by any prime on our list. So why would this be true? Well, let's just pick some prime. Let's just pick P2. If I were to try to divide this by P2, this product here is divisible by P2. So this will give me some integer when I divide it out. But 1 is not divisible by P2. So this sum would not be divisible by P2. That works no matter what prime I pick. Okay, so how does this help me? Well, from my days of doing algebra in the past, I know that a number is either a prime number or it's divisible by a prime. Thus, either this number here itself is a prime number, which could be the case, or it is divisible by some prime number that's not in this list. One of the two have to be true. And in particular, this or is actually an exclusive or, so just keep that in mind. But now this list that we created contained all of the prime numbers. Well, this is a contradiction. Thus, there is no largest prime. Okay, so a good exercise would be to write this in a formal sense. All the material is here, and you just need to put it into a slightly more formal framework. Okay, so now proof by contradiction. So I want you to read the proofs of claims 5 and 6 on page 22, and just do what Dory says and just keep reading. So now that we've looked at several proofs, I want to make a brief comment on what I expect you to get out of this material. Coming out of this week, I want you to be able to read and understand the logical structure of the various proofs that will be presented in the text throughout this course. And I want you to be able to prove simple statements via formal proofs. So since this isn't a math course, I'm not going to go very heavy on proofs. That said, on this week's homework, I will give you 6 homework problems to prove, just so that you can demonstrate that you understand how these various techniques work and to give you a chance to be a little bit creative. Okay, so that's it for this lecture. I hope you have a good day. If you have any questions on any of the material in this lecture or any of the proofs in the book that I asked you to read, then Piazza, of course, is always open, and you can feel free to attend office hours. See ya!